Hi, this is Jehong. I'm a Capstone project leader, and in the Sprint 6, I implemented a couple of great features, making a progress in the Capstone project, and I would like to introduce one by one. So the first feature that I want to show you is the extending the functionalities for summarization and translations to be able to process multiple pages. So as you may have seen the previous Sprint videos, each summarization and translation feature could only process one page. But now I extended the functionality so that each of them can process multiple pages. So now if I run this script, so this function is called passing in the starting page number, which is 7, and the end summary page 17, and the max number of sentences to be in the output, which will be 10. So this is the summary that I get starting from page 7 to 17. And this is another version using the k-means cluster approach. So the next thing is the translation feature. And if I run this script, it will ask you to enter a starting page, let's just say page 5, and ending page 7. So now the model needs to translate uh, 44 sentences in total. But since the translation feature uses its pre-trained model from Hugging Face, which has its maximum number of tokens allowed, um, we can't pass all the inputs of sentences at once. Otherwise, the model will just run overhead. So what I implemented was to set up a buffer that will temporarily store a batches of the inputs. And once the size reaches to its maximum, so the model will flush out what's inside of the buffer by printing it to the output, and it will refill another batch of the inputs that I'm sending so that the model will never run into the exceptions of exceeding maximum tokens allowed. So now, so the users can see the output, and then by the time the user is finished reading the batch of responses, it will print out another batch of responses by the model. Yeah. So this is the translation feature that I've extended so that no matter how many pages the users entered, the model will, even though it may take some time, but will try to translate each batch of inputs of sentences at a time. And the next feature is the web scraping feature. And this is the one requested by our clients. So our model will answer users' queries based on the information presented in the uploaded documents. However, not all the terms that are in the documents are brand new. Some of them might be outdated, and the terms may have changed in terms of their meaning over the time. So we want to compare their definitions against the ones found in the web scraping result. And so the beautiful soup was the library that we can use recommended by our client. And so if I run this script, it will ask you to make queries as usual. What is auto throttle, for example? And now the term will extract the auto throttle. And then, so basically, I implemented web scraping feature based on the user's query. It will extract its term, which is auto throttle in our case, and the auto throttle will be sent as a URL to the Wikipedia. And the Wikipedia, it will first go to the search page and it will go to the page that shows up on the top at the top from the search page, and then it will bring its first paragraph text. So this is the first paragraph text on Wikipedia if we look it up auto throttle. So that if we happen to unload some of the old Boeing documents and the auto throttle um, may have different meanings as times have passed, then we can compare their definitions to each other. And another quick feature, it's not a brand new feature, but I added a exception handling in the semantic search. If users make queries that are completely irrelevant to the unloaded documents, then the model will simply answer, um, it won't be able to answer. So for instance, where is Washington State University? Since we've unloaded Boeing aircraft documents, it has nothing to do with where Washington State University is. So now, as we are all expecting it, not able to find its relevant information from the unloaded documents. Another feature that I implemented was the graph-based search algorithm, so that similar to the ChatGPT, how ChatGPT behaved when the users make queries, the model will fetch its response based on the uploaded documents. But also, I wanted the model to bring up some follow-up questions. Would you like to know more about X, Y, and Z, which are that are related to your user query? And there are some preliminary steps that need to be done first before using the graph algorithm. And I need to extract all the terms, technical terms from the loaded Boeing documents. And and that's the uh, another feature that I implemented, document terms.extract. If we run this script, all the terms that are um, getting extracted from the document will be stored in the JSON file, just like a list of sentences store, including its embeddings for each page. And you can see its result in here. Uh, so yeah, so now we have the 2D list, and for each page number, the reason why it's the 2D list is each element is a list of terms extracted for its corresponding sentence. So for example, we have the term Boeing extracted for the first sentence. That's what the first element represents. And we have the second element is a list of two elements, which is a manual author, Julian Lockwood, which were the terms that were extracted for the second sentence. And the list goes on and on. And similar to the generating embeddings for the sentences, I also generated embeddings for each one of the terms. So we have a super long JSON data that will be used to generate edges connecting between um, nodes in the graph. So we have now everything ready to build a graph. We initialize the graph, and after we're gonna iterate all the terms that have been extracted, and then we will make a node with each node representing a single term. And we have an edge that connects between two nodes, and we're going to only make an edge between two nodes if we have a cosine similarity of those two terms that are above the threshold. So for instance, if I set up the cosine similarity threshold to be like zero point 0.7, anything lower than zero point 0.7 will not generate an edge between the nodes. However, if we have a cosine similarity of like more than zero point 0.7, which is indicative of high level of subsimilarities between those two terms, then there will be an edge connecting those two nodes. So that's how what it's doing right now. So if we run this script, it will generate its graph and then visualize how the graph looks like for us. So Oh yeah, by the way, this is how the graph looks like. And as you see here, there are tons of nodes and edges from the document, obviously. And so now the benefit it brings the graph algorithm is that what is your query? If I say auto, um, let's just say plain, let's just say auto throttle, then it's gonna ask follow-up questions, some of the terms that are related to auto throttle, not just auto throttle. We have throttle switch, auto throttle, throttle, throttle caution. So if I continue, like, uh, what is your query? If users make some queries like plain, then it will spit out its a list of concepts or terms that are related to plane. For example, plane flight, plane aircraft, real aircraft. And those nodes were able to be fetched because the plane had represented as a node, and then these are all the nodes that were one edge away from the plane. And one cool thing that I want to show you is if we set up the threshold to be zero point 0.9, which is we're only drawing an edge between two nodes, if the cosine similarity is more than 90%, which is highly unlikely. So if we run this script, now we're expecting the graph to be like more clear, I would say. So now, yeah, let's see. As you see here, we have a smaller number of edges drawn in here, and we can clearly see some of the terms in the middle because there are less edges representing the graph with the cosine similarity threshold more than zero point 0.9. And lastly, another feature that I implemented was to fine tune the models so that it will generate more accurate embeddings. And last time I was able to generate embeddings sentence by sentence, but in the previous sprint, what it's lacking was its accuracy since the model won't be able to recognize if the terms x and y are contextually similar if they're not shown in the adjacent places. So if even though like they're contextually have the similar meanings, but if those two different sentences are found in completely different pages, the model was expected to generate um, embeddings that make a low levels of cosine similarity. So we don't want that, obviously. We want the model to have the embeddings as accurate as possible. One way we can do that for improvement is to fine tune the models. And how I implemented the fine tuning was sort of creating a similarity pairs and the different pairs. So what I mean by similarity pairs, it will be flagged as similar because these two sentences are fetched from right adjacent to each other. So this might be the sentence previous, and then this sentence is whatever that comes right after explain Boeing. So we know we can sort of predict that these two sentences might be similar. And we also have um, able to create different pairs by bringing the sentences completely from different pages, just randomized sentences coming from different pages using the random library in Python. So if I see, for example, so these are all the examples of different pairs that have been labeled as zero, and these two sentences are completely random. These two sentences are not adjacent to each other at all. Uh, I don't know, this sentence could be from page number 5, or the second sentence coming up after could be coming from page number 22, for example. And obviously, we can they are more likely to be unrelated based on the fact that those two sentences are coming from different pages compared to the ones that are right adjacent to each other. So we will let the model take considerations of these similarity pairs and the difference pairs, and we're expecting the model to generate more accurate embeddings, which will result in more accurate semantic search and the summarizations, all that as well. Yeah, so these were all the features that I implemented in Sprint 6. Thank you.